Welcome to all my video lecture presented by Dr. A.VELMURUGAN, Assistant Professor, Department of Mechanical Engineering, Government College of Engineering, Chettikari, Dharmaburi. In this video lecture, Thermal Engineering 2, Module 3. Previously from Model 1, Model 2, Model 1, types of nozzle, friction of nozzle, flow through nozzle, effect of friction nozzle, and the mass flow rate of the nozzle. From this, in this module, we have to discuss about the maximum discharge through the nozzle and the metastable flow and the critical pressure ratio. The first title is the condition for maximum discharge in the nozzle. The rate of mass flow rate unit area M by A is equal to square root of 2000 N divided by N minus 1 into P1 V1 into P2 by P1 power of 2 by N minus P2 by P1 power of N plus 1. The mass flow rate unit area is maximum at the throat, since throat area is minimum. From the equation we can find the M by A is a function of P2 by P1 as a N is fixed according to the steam supplied. From the maximum will be occurred in the mass flow rate area and P2 by P1 is a throat. Other should be neglected. Where N is equal to 1.3, that is a superheated steam. Already I told about it, that the critical pressure is equal to R is equal to 0.578. Where N is equal to 1.135 saturated steam. For wet steam, N is equal to 1.013 plus 0.1x. For maxima and minima, therefore M by A is a maximum. When already I told about it, we have to neglect this area. We find out, finally we get P2 by P1 power of 2 by N minus P2 by P1 power of N plus 1 upon is minimum. From maximum and minimum, previously used to studied about the maximum and minimum, we have to differentiate with respect to P2 by P1 is equaling 0 for maximum discharge. Differentiate by d by d in P2 by P1 into P2 by P1 power of 2 by N minus P2 by P1 power of N plus 1 by N equal to 0. From the differentiation, 2 by N into P2 by P1 power of 2 by N minus 1 minus N plus 1 upon by N P2 by P1 power of N plus 1 by N minus 1 equal to 0. Again we have to simplify 2 by N P2 by P1 power of 2 by N minus N equal to N plus 1 by N into P2 by P1 power of 1 by N equal to 0. Again we have to simplify P2 by P1 power of 2 by 2 minus N by N into P2 by P1 power of minus 1 by N equal to N plus 1 by 2. Finally we get P2 by P1 power of 1 minus N by N is equal to N plus 1 by 2. P2 by P1 equal to N plus 1 by 2. Again P2 by P1 is equal to N plus 1 by 2 power of N divided by 1 minus N. Finally we get 2 by N plus 1 power of minus N divided by minus 1 minus N. Finally we get critical pressure ratio from throat. P2 by P1 is equal to 2 by N plus 1 power of N divided by 1 minus N. From the convergent and divergent nozzle, from the convergent section, the high pressure steam is entered to the nozzle. The Mach number is less than 1. From the throat section, Mach number is equal to 1. From the divergent section, Mach number is greater than 1. Next topic, the define of critical pressure ratio and critical pressure ratio. The design aspect for nozzle is very important. The ratio, already told about the critical pressure ratio, P2 by P1 is equal to 2 divided by N plus 1 power of N divided by 1 minus 1. N is equal to adiabatic process for index. PV power N is equal to constant. Upon the values of index N, the wet steam is N is equal to 1.113. Finally, we get P2 by P1 is equal to 2 divided by 1.113 plus 1 power of 1.113 divided by 1 minus 1.113. Finally, we get R value is 0.58. From the saturation steam N is equal to 1.135, we get 0.578. For superheated steam N is equal to 1.3, N equal to 0.546. From the design aspect, the critical pressure ratio is very important. From the schematic view of the turbine and the nozzle, we have to rotate the turbine with high speed with the help of nozzle is high velocity, nozzle speed is very high, high discharge, mass will be also high. The critical pressure ratio, the pressure at which the area is minimum and the discharge per unit area is maximum, known as critical pressure ratio. The pressure at which area is minimum and the discharge per unit area is maximum is known as critical pressure ratio. The critical pressure given velocity of the steam at throat is equal to sonic velocity of sound. The flow in the conversion quotient is subsonic. Initially, P1 is equal to P2, there is no discharge. P2 is a gradually reduced, this will cause a discharge increase gradually as the pressure approaches maximum discharge. From the graph shows from y-axis discharge, from x-axis P2 by P1, from the x value from here, for example P2 by P1, from P2 is 10, P1 is 10, we get 10, P2 is 10 bar, P1 is 10 bar, we get the value is 1. From this graph we have there is 1 means there is no discharge. For example P2 is 7.5 bar, P1 is 10 bar, we get the point is, we get the answer is 0.75. There is a little bit there, the discharge will be gradually raised. After P2 is 5.78 bar, P1 is 10 bar, we get 0.578. The maximum discharge will be occur after no changes in the discharge. The discharge will be gradually moving from this same line. That's why we have told about from the initially P1 equal to P2, there is no discharge. From P2 is gradually reduced, it causes a discharge is increased gradually as the pressure approaches maximum discharge. From the convergent and divergent nozzle, we have already told about it, that is a sonic velocity. The Mach number is the velocity of the fluid by velocity of the sound. From that convergent nozzle, the steam velocity and the sound velocity, if the steam velocity is less than sound velocity from the convergent nozzle, from the throat section, that steam velocity equal to sound velocity. From the divergent section, the sound velocity is greater than the steam velocity. Next heading we have discussed about the metastable flow. When the steam flow through a nozzle, it would be normally be expected that the discharge of the steam through the nozzle would be slightly less than the theoretical value. But it had been observed during the experiment on the flow of wet steam that the discharge is slightly greater than the calculated by the formula. The convergent part of the nozzle is so short and the steam velocity is so high, and then the molecules of the steam have insufficient time to collect from the droplets, so the normal condensation does not take place. Such rapid expansion is said to be metastable flow and produces supersaturated state. In this supersaturation, the steam is undercooled to a temperature less than the corresponding to its pressure. From the graph, we have to see about the supersaturated flow of the steam. From the Molière chart, from enthalpy and entropy diagram, that above dark line is shown for the supersaturation, that is a dry saturation line. From there is a 5 pressure P1, P2, P3, P4, P5. From process 1 and 2, that is isentropic expansion will be started from here, from process 1 to 5. From process 1 to 2, that is a theoretically it will be the isentropic expansion process. If the theoretically from it goes to the steam goes to the wet region, from the point 2, the process will be started, that is a condensation will be started. But it is not possible because of the convergent nozzle is portion is very small. The pressure will be raised very high. It will be happen from the 0.01 second. So that's why the steam will be converted for the superheated steam. The process not started. From this area is a supersaturated field. That the process, the condensation is started from the point 4 to 5. That dotted line is Wilson line. The Wilson line is suited for the scientist of name is Wilson line or supersaturated line. From the nozzle, there is a two section. One is a superheated region, another section is a wet region. High pressure steam is entered to the nozzle. From the particular place, a particular region, particular critical pressure ratio, the condensation will be started. But it is not possible to, practically it is not possible. The time will be happen from that 0.001 second. So the wet steam is not formed. It is possible. So there is no condensation for the actual conditions. Automatically the superheated steam is formed from the delivery from the exit conditions. From the graph, from the temperature entropy diagram, TS diagram, that the red line is shown for the saturation line. Here the constant pressure process is going on from the wet region, from this wet region, from this left hand side liquid region, from the right hand side superheated region. From the process, the isentropic expansions happen from the process 1 and 2. That this crosses the wet region. From theoretically the condensation will be started, but in the actual practice there is no condensation will be started because of the time will be very less. Next process will be started. That's why the condensation. But theoretically the condensation will be started from this metastable flow. When superheated steam is expanded, is isentropically it starts to condense as it's meet with the dry saturation, right? But in nozzle the velocity of the steam is very high, and hence the available time is very less. About previously I told about the time is very less, 0.01 second. The condensation does not start at point 2. For the flow from 1 to 5, the steam continues to expand in dry condition up to point 4. The steam between the state 2 and 4 is said to be supersaturated or metastable state. The flow of such saturated is known as supersaturated or metastable flow. This line is called Wilson line, is used to the saturation line for all practical purpose. Before this line, the steam suddenly starts to condensate. Thank you.